Hi everyone, this is Group Lahar. Our research question is to identify the response of boreal forest from the outbreak of mountain pine beetle.
First of all, I will be introducing the background information of mountain pine beetle. The mountain pine beetle is an insect that colonizes trees and causes them to death. The outbreak of MPB in Canada started in 1990s in British Columbia and migrated all the way to north-central Alberta in 2017. The outspread of MPB in the Jasper National Park, which is our study area, started in 2014. Under normal conditions, the mountain pine beetle are good assistants in forest regeneration. As the forest reaching the climax community, the old trees can be obstructed for young trees to develop by blocking the incoming solar radiation. Therefore, the elimination of old trees are sometimes necessary for sustainable development. However, due to the climate change and extreme temperature, the dramatically growing population of MPBs started to become harmful, especially when the beetle-killed biomass becomes fuels underlying in the forest and potentially increase the risk of wildfire. A significant change on trees after the infection is that the leaves will turn to an abnormal red color instead of green, which is easy to observe by using remote sensing image. The NDVI and NBR value are used to analyze the data in order to understand the change in tree conditions and burn severity pattern. Therefore, remote sensing tools are helpful and effective in our research.
Our objectives are first to investigate how mountain pine beetle affects the boreal trees and identify the response of the boreal trees after the Malane wildfire. Second, to find out the relationship between the increased risk of wildfire and the outbreak of mountain pine beetle. The study area is located at Jasper National Park in Alberta, Canada, and the Malin Lake inside the Jasper National Park, where the wildfire happened in 2016. The study areas are 32 square kilometers and 16 square kilometers.
This is our group project flowchart, which shows our progress. After choosing a topic with a selected study area from our group discussion, we create a boundary as well as collect data from USGS Earth Explorer website. Second, we stack all images we downloaded and clip the images to the boundary shapefile. Third, we split our group to process the NDVI, NBR, and supervised classification with change detection. And then we produce our results and graphs by randomly select and extract points from our NDVI and NBR map, create error matrix, and change detection map for our result and graph analysis. Finally, after making several group discussions, we create our final group presentation.
For image preparation, we download the image from Earth Explorer with two sensors, LiSAT 5 and LiSAT 8. LiSAT 8 imagery is used in the years between 2013 and 2019, and LiSAT 5 imagery is used from 1990 to 2011. The clip area is based on the study area. We created two boundaries around the Central Park area and the Malin Lake. Those are 32 square kilometers and 102 square kilometers. Because LiSAT 5 and LiSAT 8 have a different spectral resolution, we stack the files with different bands. In order to stack RGB, NIR, and NSWIR together, we choose band 125 for LiSAT 8 for LiSAT 5 and band 227 for LiSAT 8 according to the tables. To calculate the pixel value, we randomly selected 150 sample points in the Jasper National Park and 15 sample points in the Malin Lake. To minimize the cloud effect in Jasper National Park for all images, the sample points may not be evenly distributed in that area. As you can see in the left image, there are some areas that do not have sample points. It's because cloud covers some of the areas in different years.
There are four methodologies we applied, which are NDVI calculation, NBR calculation, supervised classification, and change detection. Firstly, we applied formula NIR minus red divided by NIR plus red for normalized differences vegetation index to select a zone of each year to detect the health or status of vegetation. The NDVI index is between 0 to 1, which indicates that the healthier vegetation will have a larger number and the less healthy vegetation will have a smaller number. Secondly, we apply the formula NIR minus SWIR divided by NIR plus SWIR for normalized burn ratio to select a zone of each year to highlight burned areas in larger fire zones. The NBR index is between -1 to 1, which indicates that the unburned area will have a larger number and burned area will have a smaller number. Thirdly, we choose the map of year 2014 and 2016 to produce supervised classification for 5 classes, which are water, snow, dead vegetation, vegetation, and rock. Due to the vegetation in 2014 was not destroyed yet, so that we choose it as a reference map to compare the class of dead vegetation in 2016. Lastly, after we classified the 2 maps with supervised classification, we chose post-classification change detection method to compare 2 maps directly to find out the changed area of vegetation to do forest fire.
Here's the result analysis for Objective 1. According to the previous research, wildfire happened in 2016. From the NDVI maps on the left-hand side, we can see a rapid decrease in 2016 until 2019. Also, from Figure 1, we can see both NDVI and NBR had a rapid decline in 2016. The NBR decreases from 0.24 to negative values. This situation has never happened in the past 15 years, and this is caused by the wildfire. Here's a pixel greenness analysis at the central fire zone. From 2002 to 2011, there's a decrease in NDVI compared to other healthy years, and the trend is irregular. This is caused by the mountain pine beetle. Mountain pine beetle decreased the boreal trees by 0.15 to 0.2 for 8 years. The trend is irregular because of the control and management of the mountain pine beetle in different years. But we can see mountain pine beetle starts to recover at 2013. For the wildfire, the NDVI decreases from 0.7 to 0.3 in 2016. It decreases the boreal trees by 0.4 in 1 year. Here's a burn severity table for NBR analysis. We can see the average burn severity is 0.5 and the maximum is 0.68. From the NBR maps on the right-hand side, we can see an increase of NBR from 2018 to 2019. But according to the previous NDVI values in 2018 and 2019, the general trend is decreasing. This situation is caused by the mountain pine beetle outbreak in the most recent years again, because when wildfire happens, we can see a trend of both decreasing NBR and NDVI. But in the situation of a mountain pine beetle, we can see an increased NBR and decreasing NDVI. Lastly, change detection shows the shift from healthy vegetation to dead vegetation. The accuracy of healthy vegetation and dead vegetation are low compared to others, because even though some areas have been affected by wildfire, they still have similar spectral trend. Thus, they are easily to be misclassified. Here's the result analysis for Objective 2.
According to the NDVI map from the Lancet between 1990 and 2019 in our study area, we can see there is a huge difference at the year 2005 and the year 2016. We have discussed about the 2016 forest fire in previous slides, so we could conclude that there is another large forest fire happened at 2005. Compared with the figure 3 here, we can see the average NDVI rapidly changed from the 0.65 to 0.49 at 1993. That could be caused by the mountain pine beetle outbreak. And there is a huge change from the 0.69 to 0.48, and this can be distributed by the NBR rapidly increase from 0.2 to 0.4. Then drop down to the 0.22 during this time could show the huge area wildfire occurs followed by the mountain pine beetle outbreak. The figure 4 shows the pixel greenness from a single pixel at Jasper National Park. It shows the relatively low value at around 1992 and 2009. Those may be caused by the mountain pine beetle, and the recovery trend was followed by around 2 years. There are 2 outstanding low values at 2005 and 2016 caused by fire with about 0.2 differences, and we can see the fire recovery from the following years. After that, there is a decreasing trend starting from 2018, which caused by the mountain pine beetle we described previously. From our result, we could understand the ongoing trend and conditions of outbreak events and the occurrence of the forest fire at Jasper National Park in recent years. Our result could be analyzed and provide useful information for local governments and environmental conservation departments. Compared to the outcome from another article from 2017, the impact caused by the mountain pine beetle should be further investigated by field approach along with remote sensing technology. These are our references related to our research group project. That's the end of our group presentation. Thank you for your watching.